Okay, so we're almost done. We're almost there. Yay. Okay, so in the last video or section or whatever, I said we were going to make a table. I lied. I decided this is a better use of time. So we're going to do it this way. So gem-diol reaction. It's different whether we do a ketone or an aldehyde. The reaction itself is going to be exactly the same, but the equilibrium is what is a little bit different. So when we have the aldehyde, when we have the ketone reacting with water and acid or base, we get the gem-diol. And the gem-diol is not going to be favored. We're actually going to favor the ketone form. However, when we have, sorry, this is really annoying. Okay. However, when we have an aldehyde present, we are going to use the acid/base and the water to actually favor the gem-diol. So same exact reaction mechanisms. The only difference is equilibrium lies here versus this equilibrium lies here. In the acetal/ketol reaction, the reaction mechanism is, again, going to be the same, whether we have a ketone or an aldehyde. I just wanted to draw both for you guys because they have different names. So if we have a ketone and we react it with an alcohol and an acid, this is important. If we react it with an acid, we get an intermediate that looks something like this. And we get our final product, which will look like this. If we do the aldehyde, we get essentially the same thing. The only difference here is we have two carbon groups, and here we have one carbon group and one hydrogen. So the one that has two carbon groups is called a ketol. The one that has one hydrogen is called an acetal. So the intermediates actually have their own names. So we have the hemiacetal and the hemiketol. The reason I drew those out is because if you do not have acid catalyst, so let's say you either have a base catalyst or you have no catalyst at all, you are going to stop at the hemi. So base catalyst or no catalyst means you stop at the hemi. And at the bottom here, I just included a drawing of the general structure of things, and I went ahead and named them for you. I don't know why the formatting looks so weird, but we do. We do. Okay. The Amine Formation, I'm going to go ahead and just, I don't know why I thought this would be like a fun little game show, but I'm going to go ahead and show you the answers while we talk about it. So the amine reaction is when we have a ketone or an aldehyde plus a primary amine. That's very important. Primary, primary, primary. That gives you an amine. We attach one nitrogen with whatever R group is present. If we have a secondary amine, we're going to form the enamine. So primary, amine, secondary, enamine. Something that Katrina actually made up was you have secondary amine. It has two E's in it. Primary amine has one E in it. Excuse me. So the hydrazone formation is when we have a hydrazine reacting to form a hydrazone. There we go. The hydrazine is two NH2s attached to one another. The hydrazone is when we attach that group to the carbonyl. So the thing is showing up super delayed, but I hope I'm not cracking up and stuff. Okay, this is fine. So before we do the oxime, we're going to talk about the phenylhydrazine and the phenylhydrazone. So the phenylhydrazine is exactly the same as a regular hydrazine. It just has a phenyl at the end. And the phenylhydrazone is the exact same as a regular hydrazone. It just has a little phenyl at the end. So if we have excess, that's where things are a little bit different. So he can say excess or he can say XS. That means the same thing. And this means we're going to make our intermediate, which is the hydrazone, and then we're going to react one more time, and we're going to have this double hydrazone looking thing. We essentially just use 2 ketones and 2 nitrogens, and we stick a ketone to each of the nitrogens. And we get that weird looking thing. You don't have to know the name of that weird looking thing. I don't know the name of that weird looking thing. Anyone's guess. I'm sure you could Google it, but I'm not going to. Okay, so the oxime formation is when we have a hydroxylamine, which is an NH2 attached to an OH. We do a lovely little reaction to attach that nitrogen to the double bond, and we get our oxime. The very, very, very important thing for you to remember here is you are always going to add the nitrogen. You are never going to add the OH. This is important because we know that nitrogen is a better nucleophile than oxygen because we know it's less electronegative and more likely to give up its electrons. Whew, that was a mouthful. And I believe we are on our last reaction. So now we have the Irid for real because we have the Wittig reaction. And we are going to go ahead and make the Irid. If we have an alkyl halide and react it with PPH3, we get this ugly intermediate. Once we react that ugly intermediate with base, we get the Irid. And please remember, there are 2 resonance structures of the Irid that you have to be familiar with, either the double bond that's neutral or the single bond that has a minus and a plus. Once we have the Irid, we can do our reaction, and I will give you the answer to this just so you have it, but I'm not going to bother going over like the box method. We're going to do the rosemary method because that's my favorite way to do it. So, we're all freaks of nature, mad scientists, Frankensteins, whatever you want to call it. So, we're going to take our ketone and our Irid, and we're going to perform a science experiment. And by science experiment, I mean we're going to chop off their arms and legs and their heads. Very graphic and disgusting, I know, I'm sorry. So, we take the 2 heads and we put them together because, you know, why wouldn't we do that? We're insane. So, you attach the oxygen head and you attach the phenyl head to get this weird looking side product. Now, our main thing, we use the heads already. So whatever we make is going to be headless, right? But we have a nice pair of arms and we have a nice pair of legs. So why not stick those guys together, right? So we're going to make our trunk, aka our body. And we have our legs, R3 and R4. We have our arms, which are R1 and R2. He doesn't have a head, but that's okay. He has arms and legs and a trunk. That's all you can really ask for. Please remember, you can stick your arms on like this, or you could go the other way. I'm not going to get up and twirl around in my room, but you can flip them around. You can flip R3 and R4 around, but you can't switch up R1 with R3. You can't switch up R2 with R4 because arms are arms and legs are legs. So we're not going to flip-flop arms and legs. We can put the arms on backwards, but we're not going to put an arm in the place of the leg. Ta-da. I feel like this reaction isn't as complicated as I thought it was when I made up the rosemary method, but I refuse to give up the rosemary method, so I hope you enjoy. That's it for chapter 16. We went through that really, really fast. So, any questions, comments, concerns, anything like that? If no question, I shall move on. So now we are in chapter 17. So chapter 17 is a lot of the same concepts as chapter 16, except now we have a leaving group. And we know in these kind of reactions, all we do is label the leaving group, we label the nucleophile, and we replace the nucleophile with, we replace the leaving group with the nucleophile. Bam. Same thing here. We label the leaving group, we label the nucleophile, and we replace the nucleophile with the leaving group. Bam. That's all there really is to this chapter. If you see a leaving group and a nucleophile, it's probably going to be one of these reactions. Okay, making acyl halides. This is really important because you cannot make an acid halide through a regular old nucleophilic substitution reaction. You need PCl3, PCl5, SOCl2, COCl2. You need one of those reagents. And all those are going to do is replace the OH with the halogen. And you will not ever be able to create an acid halide via nucleophilic acyl substitution. And the reason is because acid, or I'll say acyl, halides are much too reactive. They're so reactive. You can't make them through nucleophilic substitution. They don't want to do that at all. The next thing in chapter 17 was lactones and lactams. So, remember, lactone is a cyclic ester. O is for oxygen. A lactam is a cyclic amide. So am for amide. And when we name these guys, we start here at the alpha carbon. We label alpha, beta, gamma, delta. And the highest letter is what names this guy. So alpha, beta, gamma, alpha, beta, alpha. Same exact rules apply for lactams. Okay. Making lactones and lactams and breaking lactones and lactams. I'm not going to do the step-by-step reaction just because we covered that like a week ago in SI and I don't want to spend too much time on it, but I will cover like the basics. So when we're making lactones and lactams, we know that we have to have our nucleophile and our leaving group on the same carbon chain. So this is our nucleophile. We get rid of that hydrogen, and we know this is our leaving group. The important part here is to count your carbons. So 1, 2, 3, 4. And oxygen is going to be in the ring. So I'm going to say 5. So I draw out a 5-membered ring with oxygen inside of it. And 1, 2, 3, 4, 5. Cool. On carbon 4, I have a methyl. And we have Cl out here as a byproduct. Another example. We have our nucleophile. Get rid of the hydrogen. We have our leaving group. So let's count. 1, 2, 3, 4, 5, 6. So let's draw a 6-membered ring. One, 2, 3, 4, 5, 6. Cool. On carbon number 4, we have a methyl. And that's it. So this is how we make lactones and lactams. It would be the same exact thing if we had a nitrogen, same mechanism and everything. It would just be called a lactam instead of a lactone. So, breaking lactones and lactams, same type of reaction, except now we take the ring and we break it open. So, we know this is the leaving group. And we know that this being the leaving group means that this bond is going to break. So it opens this way. We know that this guy is the nucleophile. Why is my screen being so weird? Okay. So first things first, I'm going to draw a 1, 2, 3, 4 membered chain. On carbon 4, we have an NH2. And on carbon 1, we attach the nucleophile, which is this guy. So the leaving group leaves this, right? It has to leave somewhere, but it can't completely leave the chain because it's still attached at carbon 4. So a lot of students will get confused about that. So the leaving group leaves the carbonyl, but it can't just leave this molecule completely because it's attached to carbon 4. And this is more of the same, so I don't want to do that again. All right. Chapter 17 is done. Now we go on to chapter 18, which is all about enolate chemistry. So, these two are just the tautomerization reactions, and final tryout. Okay, I felt bad. All right, so we have these alpha carbons, and we have alpha 1 and alpha 2. We have to figure out which alpha hydrogen we are stealing. We're going to pick alpha 2 because it is more substituted. So the more substituted side is the one that's going to be taken. So bam, bam. And we end up with a negative charge here and only one hydrogen. Something cool we can do is resonance. We can go like this, bam, bam. And resonance, will produce a negative charge right here. We still have that H here, and now we have a double bond here. So this set of resonance structures is called the enolate. And we are going to react the enolate with the H2O molecule we created. And it's going to go ahead and steal that red hydrogen back And we're going to end up making this lovely thing. And this thing is called an enol. So the ketone and the enol are a pair of tautomers, and the enolate is a pair of resonance structures. For more about that, please watch the SI session about tautomerization and everything. Now, chapter 18 can seem really overwhelming and difficult, but in reality, it's not too bad. Racimization. Okay, for racimization, just know, I'm not going to draw out like all the different steps again, but the concept that you have to know is in order to do a racimization reaction, you need a chiral alpha carbon with a hydrogen. So you need to have a chiral alpha carbon that has a hydrogen on it. This example that I've drawn out was supposed to just be a trick because this guy is not a hydrogen, it's a methyl. So this does not have a chiral alpha hydrogen. If we had this, then we could do a racimization. All right, the important reactions for this chapter. We're going to start with the halogenation. So many halogenations. So we have acid and base catalyzed. So in the acid catalyzed, we end up with this. We add 1 bromine. With the base catalyst, we're actually still going to look at that most substituted side, but now we're going to add as many bromines as we have hydrogens. In this example, there were 2 hydrogens on this side, so we end up with 2 bromines attached. Now, what if we have excess and we only have this primary side? And by primary, I mean there's 3 hydrogens available, right? There's no better side. So like in these examples, we didn't like this side because this side was a lot better, but here we have no choice. And I told you when we have base, we replace all of the hydrogens. So we end up with this WAMO, which is a halohydrin. And we actually will end up reacting this with OH to get this. Plus CBr3. Yeah, this is the haloform reaction. So this specific type of base catalyzed halogenation is called the haloform reaction. And so I will zoom out so you can see all 3 of these guys on one page. Okay. So now we're going to the Halides-Zelinsky reaction. Oh, someone said wait. Okay, I wait. You're very welcome. Okay. So the Halides-Zelinsky reaction, I'm bad at pronouncing it, but I will write it for you, and I will probably spell it wrong. Halides-Zelinsky. Sure. Alrighty, if I've said it once, I've said it a bajillion and a half times. PBr3 is turning an OH into a Br. Br2 takes an alpha H and turns it into a Br. And H2O is actually going to take a Br and turn it into an OH. So we end up with a bromine here. And in the intermediate, we had a bromine here, but when we have the OH, we change it back to an OH. In an example where we don't have any H2O present, we are actually going to stick with 2 BRs. So we get this. So if we have H2O, it turns into this. If we don't have H2O, it stays like this. Someone asked if I will be sending this out. So it's not my best work. It's really ugly and it's really hard to read. But if you guys really want it, I can send it out. It's up to you. Please do. Okay. For you guys, I will do it. But I'm not going to make it pretty just because I will obsess over it for days at a time. Okay. Coolio. So the last one we're going to talk about. So someone said, does it matter which BR is changed? Yes. And so let me actually erase this and write it better. So we're specifically going to change this BR to an OH. You're welcome. Okay, so alkylation is fun, if you can spell it right. Okay, so for an alkylation, you're essentially using this guy as a base, and you're using your alkyl halide as your R group. So you're going to take this part of the alkyl halide, and you're going to stick it onto the alpha carbon. So you get 1, 2, 3 carbons. Ta-da! That's all there is to it. So you're going to take your R group off your alkyl halide and you just stick it onto the alpha carbon. And I always number them. So I will number them for you. 1, 2, 3. Bam. So what you do need to keep in mind is something called LDA. So LDA is a bulky base. And so if we had this exact same reaction with LDA, you would keep this R group. This is your R group. That doesn't change. But The bulky base means you can only add on the less substituted side. So only when you have LDA, you are going to add your group to the less substituted alpha carbon. So you would get 1, 2, 3. Any question about the alkylation? Okay, cool. So for this reaction, I'm not going to do both. I'm just going to do one of them, and I'm going to do them real quick because I do want to do some practice problems. So you see alkylation, substitution, decarboxylation. If you want the step-by-step for this, please watch that SI session. So we are in the first step going to alkylate. So we add this group, and I'm going to actually do that in green. We add CH2, CH2, pH. Next step, we are going to do a substitution. So we take this guy, and all we do is replace the ester with NOH, because that's how you do a nucleophilic substitution. Last step, we're going to do a decarboxylation, which is a little bit weird, so we will draw it out. So this side is going to stay the same, because I said so. This side is going to get flipped around, again, because I said so. No, just kidding. The real reason is because you want the hydrogen to be able to hydrogen bond with the carbonyl. So what's going to happen is this O is going to steal that hydrogen, bam, which causes this bond to break, which causes this bond to break, bam. So you end up with the double bond now in a different spot, and I underestimated my space again. So now I'm just tilting this up so it's neater. So we made a new double bond right here, and we made a new bond to this blue hydrogen. And our side product is going to be CO2. Ta-da! Decarboxylation is a lot. This reaction is a lot. So please watch the most recent SI session. We do cover that, but I don't want to spend any more time on it because I do want to do some practice problems. I feel like I'm not even speaking English at this point. I'm just blah, 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 blah. Okay, let's practice problems. Okay, so we started a packet of practice problems in SI last time, which was like yesterday, I think. And so today we're just going to continue and do whatever questions we didn't have a chance to look at. So we're going to start at the bottom, just because we didn't get to any later chapter questions or any really difficult questions. So, okay. This one is a weird one. It does usually end up on the exam. So which carbon bond would you expect to be the longest? So we know that single bonds are the longest bonds, and triple bonds are the shortest. And so the longest bond is going to be the one that's single bond, and it's furthest away from any triple bonds. So this guy is furthest away. This one is right next to a double bond. This one is in between a triple bond and a double bond. So this one is going to be the longest. So E is our answer. Coolio. So this next one, which synthesis of a Grignard reagent would fail to occur? So we're looking for the one that will not happen, right? So we zoom in, and this is one where knowing your functional groups is going to save you a lot of time. So this functional group is an ether. So it looks like so, CH3, O, CH2, CH2, Br. B is just an alkyl chain, so I'm not going to bother drawing that out. This is a carboxylic. So it looks like this. And this last one is just a benzene ring with a bromine on it. Right? So in a Grignard reaction, which one of these will fail? And I'm actually asking you guys this question because we did just talk about it. C, absolutely. And the reason this is the correct answer, this will not happen because we have an acidic hydrogen. So that Grignard reaction will not occur as written because of the acidic hydrogen. Awesome. So here, just in case you want the question with it. Alrighty. We're going to skip that one. Not important. Okay. Which one of these dienes is cumulated? Please do not draw all of these options out. This is going to take you forever and a half. So cumulated, we know, looks like this. So we can pretty much find that in here, right? These guys are too far away, too far away. Ooh, too far away, too far away. So the answer is C. We know that this is isolated. They're really far apart. This one's isolated. They're really far apart. And if we have two double bonds with one C in the middle, that means they are conjugated. Okay. Bum, 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 bum. This is a good one. So, NaBD4. This looks a lot like NaBH4. And we know that's a reducing agent. So, odds are we're doing a reduction, right? And we're reducing a ketone. So the reason this D is important and why it's not a hydrogen is because he wants to know that you know where that H attacks. So D will attack here. And so we get CH3, COH. I'll do it like that. D, CH3. Because this O minus is going to take a hydrogen from H2O, and the deuterium will be added to this carbon in order to reduce the carbonyl. So let's look at the answer choices. OD, no. OD, no. Double bond, what the heck? No, right? Now this one doesn't even have a deuterium anywhere. What the heck? Garbage. So we're stuck. Actually, we're not even stuck. B is the only answer that makes even a little bit of sense. Because it has our OH and it has our D. Ta-da! That's how I like to solve reaction problems on the exam. Super lickety split. And yes, I can definitely explain again. So, NaBH4 is a reducing agent, so I know we're doing a reduction. And I know that a ketone gets reduced into a secondary alcohol, right? And I know that the H from NaBH4 is what does the reducing, right? And since we have NaBD4, we have to use a deuterium instead of a hydrogen, right? So we know that if we use a deuterium to reduce, we're going to add a D and we're going to reduce this to an OH. So when we look at the answer choices, we're looking for one that has an OH and a D. This one has an OD, it has to be wrong. This one has an OD, it has to be wrong. This one doesn't have a deuterium anywhere, that has to be wrong. And this one has a double bond still, so there was no reduction. So the only one that could have worked was B. That was still kind of fast, so I can definitely repeat it if you want me to. Okay, cool. Look at the naming. I don't want to spend time doing a lot of naming questions, but if you know the naming stuff we talked about in my handouts and that he talked about in his PowerPoints, you should be good to go. Actually, I lied. We are going to do tosylate, but that's the only naming one we're going to do. Because people mix up mesylate and tosylate all the time. Remember, this guy is toluene. So tosylate is just toluene with the funky tosylate, mesylate, tosylate group. So before I tell you the answer, I actually want to see if you guys at all remember what it looks like. So between these reagents, which one is a tosylate? Okay, someone said they think it's 3. Someone said they think it's 1. Ooh. Okay. All right. So we were, well, okay. So I see where you guys chose 3 from. So let's talk about it. So the biggest thing that we have to remember is that tosylate looking group is, come on, dude, why are you like this? Is going to look like S, O, 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 R group. So if we just attach these two things together, we're looking for something that looks like this. And the only one that fits the bill is number 1. So just remember, the O comes after the S, and there are 2 oxygens here. A lot of people get tripped up on this one, so please know what mesylate and tosylate look like. S is just sulfur. So I think you mean this one. What is this one called? So I don't actually know what this is called. Sorry. I don't truthfully know what this is called, but if you know what this one is called, you should be good for this exam. I can look that up for you, though. Okay. We did those ones in SI. Let's do this guy. All right. So we have PBr3. And we know, because Rosemary said so, PBr3 turns OH into Br. And then we have Mg. So this is a Grignard reaction, right? So we started out with this. We turn it into this. And then we turn it into this. So this is A. This is B. And I did it really fast. But basically, I turned the OH into a Br. And then Mg kicks off the Br and leaves the negative sign here. Right? So now that we have this, we're going to react it with this. And we know that this case does not matter which side we open up because they are exactly the same. So let's do this plus this guy. We attack, open up. So we break this bond. And we get, bam, bam, a bond to carbon 1, a bond to carbon 2, a bond to O minus, and here we have C. C gets protonated by H3O plus, and we get this guy. So which of the following answers represents what we drew? C, yes. Ta-da! I know this one was fast. Do you guys have any questions on this one? Okay. All right. So which of the following compounds will not be reduced by LiAlH4? So we look, LiAlH4. This is a strong reducing agent. Therefore, we know that it reduces group 1 and group 2. So this guy should be able to reduce everything, right? So let's look at these functional groups. Here we have an aldehyde. Here we have a carboxylic acid. Here we have an ester. And here we have a ketone. So far, all of these guys look good. All of these should be reduced. And then we have an alkene. Did we talk about alkenes in Orgo 2 being reduced? Yay or nay? No! So the answer to this is A. Because we know that LiAlH4 reduces group 1 and group 2. All of these guys, all of these answer choices fit into group 1 and group 2, except for A. Therefore, A will not happen, and that is our answer. Did my logic make sense for this one? Ish, maybe. Okay. I think we have time for like one more. All right, let's do this one. Which of the following compounds would have the highest boiling point? And assuming that they all have approximately the same molecular weight. So we're not looking at the number of carbons here, we're looking at other stuff. So this guy is just a straight carbon chain. Cool. This one has an alcohol. This one has an ether. This one has a chlorine. This one has an ether. So alcohol, alkane, ether, ether, chlorine. So someone answered, so wonderful. Yes, it is B, because alcohols have the highest boiling point between the ethers, or I guess against the ethers, and then chlorine and alkanes, dude, we didn't even talk about that. You know, they weren't even in the competition, right? We canceled A and D out automatically. And then we knew that alcohols have a higher boiling points than ethers. So we know that B is the correct answer. Ta-da. Okay, let's see if there's any... No. Okay, so we covered all the other super important questions that I wanted to cover. And we are right on time. Yay! I'm so proud of us. We went through that so great today. Yay us. Okay, so any questions, comments, concerns about anything at all? It could be about how the exam goes. It could be about how to study. Hit me. I'm here. Or you can email me. Aww. Okay. Well, I'll stick around if anyone has any questions, but to the online people, I bid you goodbye and happy studying.